This lesson is going to be looking at curving scores. In essence, we're starting with a set of data with a given mean and a given standard deviation. And the question is, can those numbers be converted to get a different mean and a different standard deviation that better meets the needs of the person that's studying? So here's a question. How could a professor fairly curve scores at an examination? In essence, he doesn't think the mean or the standard deviation is a fair representation. So the question is, how can we change those statistics? And this idea generalizes beyond test scores. It's just the simplest metaphor for us to use when we're discussing converting data sets. So here's the following set of scores. So the professor graded a 40-point test, and he has the following scores. Typically what a professor would do is he would divide by 40 and multiply by 100% to assign a percentage to each test score. But we want to try something a little bit different. We're looking at those 40 points and recognizing there is a mean of 28 and a standard deviation of 7.04. And the professor wants to start with those numbers and construct numbers that will better meet his needs. So what kind of a mean and a standard deviation would he like? So this question is saying we want to curve the test scores so that the mean is 74 and the standard deviation is 12. So here's the data from Minitab. The mean is 28, standard deviation is 7.04. The question we're going to ask is, what would happen if all the elements of the data set were doubled? So you'll notice I have the 20 numbers in C1. You can see them here if you'd like. I'll say print C1. And you can see the 20 numbers in that data set. If we doubled all those numbers and we said let C2 equal 2 times C1, we get a different set of numbers, and you know what those would look like. What would their descriptive statistics look like? So we're going to say describe C1 and C2. You will notice the mean went from 28 to 56, so the mean doubled. The standard deviation went from 7.04 to 14.08, so the standard deviation doubled as well. So it appears as if multiplying by a number is going to mean that the mean will be multiplied by that number and the standard deviation will multiply by that number. So here's our big fact. Multiplying a data set by a factor, in the last example we multiplied it by 2, causes the mean and the standard deviation to be multiplied by that factor. In the last data set, the mean and the standard deviation were both multiplied by 2. Now what happens if we add a number to both elements in a data set, or to all elements in a data set? So this time I'm going to say let C3 equal 10 plus C1. So all the elements in C3 are 10 more than all the elements in C1. I have some other things there that I'll erase now so that those don't confuse anybody. So we'll take a look at the numbers in C3. 50, so it was 40, now it's 50. Was 39, now it's 49. So we added 10 points to all the values in C1 to create C3. If we describe C1 and C3, how do the descriptive statistics change? Notice we added 10 and the mean changed by adding 10, but when we added 10 the standard deviation stayed the same. And that shouldn't really surprise us because the standard deviation is a measure of spread. So if we add 10 to every element in the data set, the spread doesn't change, but the average will change. So our next rule is that adding a number to a data set will increase the mean by that number, but will not change the standard deviation. Current standard deviation 7.04, desired standard deviation is 12. Which number must be multiplied by 7.04 to obtain 12? To do that, we recognize we've got to multiply 7.04 by something to get 12. So we're starting with an equation. 7.04 times x equals 12. Dividing both sides by 7.04 gives me a value of 1.705. So we've got to multiply that data set by 1.705 to obtain a standard deviation of 12. So our data set is in C1. Let me erase C2 and C3. I'm going to say let my new version of C2 equal 1.705 times C1. Now, if that's going to happen, both the mean and the standard deviation should change, but I want to fix the standard deviation first. Once I do that, I'm going to say describe C1 and C2, and you will see that the standard deviation is essentially 12. 12.01, close enough for me. But my mean isn't quite where I want it to be. My mean is 47.04. At this point, I can add something to both sides to get what I'm looking for, to get the required mean for the translated data set. So our current mean is 47.74, and the desired mean is 74. And the question we have to ask is, what must be added to the data set to obtain that mean of 74? So what number do we need? And as we saw in our example, when we add something to a data set, the mean changes. So we've got an algebra question to solve. It, of course, is 47.74 plus y equals 74, subtracting 47.74 from both sides, and that gives us 26.26. That is what we have to add to the data set to get the mean of 74. Now, we fixed the standard deviation earlier, but adding 26.26 will not affect the standard deviation. Okay, so let's go to Minitab and see how that's going to work. So currently in C2, we have a mean of 47.74 and a standard deviation of essentially 12. So what are we going to do? We're going to add that value, 26.26, to that data set C2. So we're going to say let C3 equal 26.26 plus C2. And now I have a new data set. And looking at that, we can say describe C1, my original data set, and C3, my curved data set. When we do that, what do we get? A mean of exactly 74 and a standard deviation of essentially 12. Now, the question I have for you is, was that a fair way to curve the test? Let's take a look at the original scores together with their curved scores. So the first person had 40 out of 40, which in most cases would be 100%, but his curved score was only 94.46. The second person had a 39 out of 40, again, which would be significantly better percentage-wise, 92.7. So this scheme seems to be penalizing the folks at the highest end of the list of scores. At the lowest end, 20 out of 40, this person should have gotten 50%, but instead is at 60. So we recognize the folks at the lowest end are actually doing better with this curve tests. So this strategy is negatively affecting the best scoring students, but positively affecting the weakest scoring students. So a question you can ask yourself, is this really fair? I would argue no, and the reason is that the standard deviation tells me how far apart the people are spread, and if you shrink that standard deviation, again, you are pulling the best students in closer to the mean, and you're pulling the worst students in closer to the mean. And I think you could argue that that's not really the fairest way for us to curve test scores. But this is a nice way to go ahead and change data sets. Given a certain mean and a certain standard deviation, you first multiply to get the standard deviation that you need, and then you add some number to get the mean that you need for that data set.